Okay, thank you for that. All right, well, hello again, everyone. So, in that first part of my lecture, we talked about energy-based arguments to get some handle on how large gravitational wave amplitudes might be, but that said nothing about neutron star structure and what we actually, how big we think these amplitudes might be on the basis of sort of realistic physics. So that's what we're going to talk about now. Equation 27 is just a parameterized formulae for gravitational waves from a mountain. So you can tell that because you can see there's an ellipticity epsilon sitting in it. Parameterized in terms of a value of 10 to the minus 6, which isn't totally random. We'll come back to that in a moment. So the question is, why wouldn't epsilon be zero? I mean, after all, even a rotating fluid, right? Its lowest energy configuration, it's just a simple perfect fluid, would be to be perfectly axisymmetric. Why should it be non-axisymmetric in the first place? Well, there are two things that could be going on. First of all, neutron stars have got a solid outer crust, and solids can support strains. So that's where the mountain could come from. More speculatively, people think that it's possible that there might be solid cores in stars as well, in which case you could have a non-axis symmetry there as well. But then the second possibility is magnetic forces. We know from radio pulsars that neutron stars have got magnetic fields. They can deform the star. So let's have a think about these two sorts of arguments in turn. Let's start with the solid bit. So in other words, with elasticity. So here is a simple way of thinking about this problem that actually gives you quite a lot of insight. So suppose, so these little squiggles you can see here, these are neutron stars with the outer crust, the outer 10% or so indicated. So imagine that we had a neutron star on the left, and it's sort of born with some large ellipticity, or let's call it a blakeness, epsilon naught. So as if we sort of scratch with our hands, we've pushed it, maybe it's sort of hot and molten crust at that point, we pull it into some highly non-spherical shape, parameterized by a blakeness epsilon naught, and then maybe let it cool and the crust solidify. So the crust wants to have that shape there, epsilon naught. If we were to then take our hands away, what would actually happen is that the crust would relax to a much more close to spherical shape with some actual ablateness epsilon that would be less than epsilon naught, because gravity wants to try and make everything spherical, right? So the minimum gravitational energy would be for a spherical star. So there's some sort of energy competition between the elasticity that wants to make the star highly deformed and gravity that wants to make it spherical. And that's the thing that we need to try and understand to get an idea of how large these mountains might be. So there's a simple argument that you can do by writing down the energy of our neutron star as a function of its ellipticity epsilon. So that's what we've got here in equation 28. So we're saying that this energy is what? This is a perturbative expansion. So it would be the energy the star would have if it were perfectly spherical, plus two extra pieces. The first is the sort of perturbation in gravitational binding energy. So this quantity A is of order, this is just the back of the envelope estimate, right? So I'm not worried about particular coefficients. This A is of order the gravitational binding energy of the whole star. So it's of order GM over R squared. So it's about 10 to the 52 ergs for a realistic neutron star. We get a term of the form A epsilon squared, because this energy, we know by symmetry, has to be minimized when epsilon is zero. So epsilon positive, say, corresponds to pulling the star out into some oblate shape. It's a sort of short and fat. Epsilon negative could correspond then to pulling the star into some prolate shape, so long and thin, like a cigar. Well, either of those, both of those configurations would have a bigger gravitational energy than a spherical one. So that's why this epsilon has to come in, not linearly, but with a square there. Then there's also the elastic energy. So what we've said is that the elastic energy is minimized when the actual shape epsilon is equal to this shape that we've given it at birth, epsilon naught. And so the elastic energy perturbation has to be quadratic in this difference, because this elastic energy has to be minimized when when epsilon equals epsilon naught. And now this coefficient here will be of order the Coulomb binding energy of the solid phase, which will be of order the shear modulus. The shear modulus is basically a binding energy per unit volume of a crystalline lattice times the volume of the solid phase. If you put numbers in there, you find you get something more like 10 to the, for the crust, you get more like 10 to the 47 ergs. That, it depends on exactly how thick the crust is and how strong it is. But basically, you find that B is much, much less than A. So in other words, gravity is in some sense dominant in determining the shape. And there's a lot more energy in gravity than in elasticity here. So it's difficult for the elasticity to compete with gravity. And also this difference here, epsilon minus epsilon naught, that's like the mismatch between the actual shape and the shape of the crust that would minimize the strain. So that can't be any bigger than the breaking strain of the crust. So you actually get quite a lot out of this model. What we're saying is that the actual largest mountain that a neutron star could sustain is of order this ratio of beta A from the last slide, which I've written down here in terms of the shear modulus, the crustal volume and the gravitational binding energy, times the breaking strain of the crust. So the breaking strain is if you took a bit of crust, bent it through some angle, how large an angle can you bend it through before it breaks? That's not well known. That's less well known than the shear modulus and volume of the crust. Shear modulus is relatively well known. It's about 10 to the 29 in CGS units. Breaking strain is more difficult to get at, but some people have attempted it though. This picture that you can see here at the bottom is it's from some molecular dynamics simulations by Horowitz and Cadell. And what they found was that actually the breaking strains that they were finding were actually sort of building a piece of crust and artificially shearing it. Those strains were rather large. They were about 0.1, which is bigger than people had thought. And the reason for that was that the pressure is very high in neutron star crusts, and that tends to disfavor having defects like voids or dislocations in the crystalline lattice. It makes it difficult for dislocations to propagate. So that's why I've parameterized the breaking strain in units of 0.1, so quite a large angle before it breaks. There are big caveats to this. The simulations of Horowitz and Cadell lasted some small fraction of a second of real sort of neutron star time, and it could be that plastic relaxation occurs on longer time scales. So you need to treat this with caution. But what this is telling us is that to some sort of first calculation, maybe you could get mountains as big as 10 to the minus 6 on a neutron star. So this is now like a theoretical microphysics-based estimate, quite different from those energy-based upper limits that we talked about before. That was just the back of the envelope argument. If you really wanted to do this properly, then I've sketched out here how in Newtonian gravity you would do it. Equation 30 is just Newton's second law for a static object. So the left-hand side is 0, there's no acceleration. And the right-hand side are all the various forces that we've got. So the first term on the right is the force due to Newtonian gravity. Second term is the force due to pressure gradients. And the last term is the force due to is the elastic force built out of the elastic stress tensor. So the shear modulus enters in that. I can see there's a question. Do you want to go ahead, Garadat?
Yeah, so question from your previous slide related to molecular dynamics simulations. So there they consider the neutron star to be made up of particles. And what kind of interaction they might be having? It is a purely gravitational interaction or?
Yes, so no, it was purely electromagnetic here, I think. So for this calculation, the gravity is not important. So here, what they care about is I think it was some sort of screened electromagnetic interaction between the particles.
I see, right. Yeah, for shear modulus. Okay, thank you so much.
It's okay. So then to keep listing the equations that we need, you also need equation 32. So that's just relating Newtonian potential to the Newtonian gravitational potential to the mass density, and you need some equation of state, some pressure density relation for the fluid. So you can put those together and solve them and do a more careful calculation, and a few people have done that. Of course, you should maybe be doing this in GR, and Gittins and Anderson did that recently. They actually found significantly smaller maximum mountain sizes, 10 to the -8. Other people have done it in slightly different ways and got slightly bigger numbers. These calculations are quite sensitive to how exactly they're done. Well, it suggests that maybe the back of the envelope is perhaps a little optimistic, and the realistic maximum size might be somewhat smaller. But I think people are still working on this problem. So it is actually possible to get significantly larger maximum ellipticities if you allow for more exotic interiors to neutron stars. And so, for instance, some people have speculated that you could get solid quark cores, or even have solid quark. In fact, maybe neutron stars aren't neutron stars, maybe they're quark stars, and they could even be solid quark stars. And the significance of the quark bit is that you can then use not just electromagnetism, but the strong nuclear force to try and build your mountains. And that's why these numbers that you can see in that second bullet point are orders of magnitude bigger than the previous estimates. So our previous estimates from the last couple of slides, we're just using electromagnetic forces to build mountains. If you have got a solid quark star, you can leverage on the strong nuclear force, and that I've even seen a number as big as 10 to the -1 in the literature. So you could get very large mountains indeed, or at least the maximum size, limited by the strength of the actual solid, could be as large as 0.1. There are variants on this. People have talked about crystalline color superconducting quark matter, so other possibly arguably even more exotic phases. So the point is, the maximum mountain size could be very large. Even with these sorts of calculations, it's still not quite what we want, because what these are telling us is how large the mountain might be, or the maximum size it could have, as limited by the matter itself. But that is quite different. It's logically completely different, really, from saying how big the actual ellipticities or mountains are. So just because, say, the crust is strong enough to support a 10 to the -6 mountain, it doesn't mean it does. I mean, the star could be born almost perfectly axisymmetric, and it might then evolve in a completely axisymmetric way. So what we've got so far really are bounds that come from the microphysics, but they're not really estimates of the mountain sizes themselves. And that's a much more difficult problem to attack. And there haven't been an awfully many different ideas on this. There was an interesting suggestion from Bilston back in 1998 to do with temperature asymmetries. And it's sketched out in this little picture here. So the idea here is that this is a cross-section through part of the neutron star crust. So the center of the star would be somewhere off below the bottom of the slide. You can see at the bottom of this picture the crust core interface. So it's neutron fluid below. Here's the ocean up here. So this is the outside of the star. This is some cross-section just through the crust. And the idea with neutron star crusts is that they've got the sort of an onion layer structure, and you've got different nucleus species like A1Z1 over a certain density range. And then as you go deeper in the star, you make a transition to some different nucleus species. And it's the equation of state, the composition, all part of that tells you, exactly what nuclear species you get and at what density this transition occurs. Now, if the temperature is the same everywhere, then the transition between these two different species would occur on a sphere of constant radius on this dotted line. What Bilston pointed out was that if, say, this left-hand bit of the crust is hot and this right-hand bit is cold, so there's some sort of lateral temperature asymmetry, then you don't have to go quite as deep into the crust to make the transition between one nucleus species and the next. And equally, where it's colder, you have to go deeper to make that transition. So you get what he called a wavy capture layer, or wavy transition layer. And so that was a demonstration that if you've got temperature gradients, or the right sort of temperature gradients in neutron stars, you can build a mountain. So that was interesting and created a lot of excitement, but you still, in a sense, it just pushes the question back one deeper. What would create that temperature asymmetry in the first place? And I think it's fair to say that's still an open question. A PhD student of mine has done some work on this, and some colleagues in Poland have thought about this as well. But basically, I would say for people that are sort of learning about modeling continuous wave sources, this issue of actually building realistic mountains, how you would do it, so not upper bounds, but estimates, that's in its infancy, and that's something that would be worth thinking about. I think that's something we need to invest more time in. So that's it in terms of elastic mountains. As I said, there's another. Sure, go ahead. Did you want to say something?
Arunabha, please go ahead. Yeah.
Hi, Ian, sorry to interrupt. I had a quick question just to understand the figure in last slide. Yeah, so this ocean that you refer, is it in the crust? Is it a solid crust, or it's a part of the fluid core itself?
So the ocean, by definition, that's liquid, and that's sort of at the top of the crust. So the idea is the solid crust is this shaded bit here.
Mm-hmm.
But in reality, there'd be more than one, or rather more than two different species. There might be like 20 or 30 different nucleus species. So this is a simplified picture, but the idea is it's fluid up here in the ocean, and outside the ocean, it's the vacuum and the rest of the universe. This shaded bit, most of this picture is the solid, and then inside the core, it's neutron fluid, so down below the picture.
Okay, I see. Maybe follow-up question later.
Sorry, say that last thing again?
Yeah, so I had few follow-up questions, probably I can ask later, maybe after that.
Okay, that's fine. Yes, I was about to move on to magnetic fields. Where have I gone? Yeah, okay, so let's now think about magnetic fields. So we know for sure that radio pulses have got magnetic fields, because we think it's the magnetic fields that are important for the radio pulse production mechanism. In fact, we've got estimates of magnetic fields in many stars, and some have got magnetic fields of 10 to the 12 Gauss. That's a sort of a typical value. There are some, like the magnetars, that have got fields more like 10 to the 15. There are others with somewhat smaller fields, but it does seem that magnetic fields are pretty ubiquitous in the world of neutron stars. One can again just make a simple estimate of what sort of mountains they might produce. The reason that they produce mountains at all is that if you've got a magnetic field in a fluid, you get a Lorentz type force acting on the fluid. You can think of it as like a tension force acting along the magnetic field lines. It turns out that the sort of ellipticities that you get from magnetic fields come from taking the ratio of the magnetostatic energy. So that's the thing that you can see in the numerator of this equation here. Taking the ratio of that to the gravitational binding energy, that's the thing in the denominator. If you put in some realistic numbers, or a realistic magnetic field, you get a disappointingly small mountain of about 10 to the minus 12. So much smaller than lots of the ellipticities that we've been talking about previously. It's believed that if your proton fluid in the interior has formed a type 2 superconductor, then the magnetic field gets sort of packaged into flux tubes, and it's believed that this can increase the tension by about a factor of 1,000, and you can get somewhat larger mountains that way. Still not enormous, but potentially interesting. But generally, these numbers are quite small. But there's a caveat to be attached to this, which is that all of the observational evidence we have about magnetic fields in neutron stars really is to do with pulsars, and it's to do with the external magnetic field. We don't really know how strong the internal magnetic field is likely to be, and it could be, maybe it's wishful thinking, but it could be that the internal magnetic field is much stronger than the inferred external field, in which case, maybe some of the numbers on this slide could push into an interesting regime. And the only way to confirm that really is to detect such gravitational wave emission. Again, let me just give you one slide on how, in principle, one would do this calculation more carefully. Equation 34 is, again, Newton's second law with no acceleration. We've got pressure forces, we've got gravity forces in the second term, and then we've got these, as I say, Lorentz forces, J cross B, where J is the current density, or curl B cross B terms. So this is the deforming force, this last term, the magnetic force. You couple that again to Poisson's equation for the gravitational field, you have an equation of state, and the solenoidal constraint that the divergence of the magnetic field is 0. So that's a well-defined problem that you can go away and try and solve, and people have done that. There's actually something of and if you do that, you confirm that the back of the envelope estimates from the previous slide are roughly correct. But there is something of an embarrassment in this field, which is that the magnetic fields that you typically find when solving this static type problem turn out to be dynamically unstable. So what I mean by that is if you take one of these solutions to these equations, and then you try and evolve it forwards in time with just tiny, tiny little perturbations in your initial data, you find that it's unstable. All hell breaks loose. And within a short period of time, the star's deformed into a complete mess. In other words, they're not dynamically stable solutions. And people have tried doing this in GR as well and got similar results. So I would say that this is another interesting and open problem in terms of CW source modeling. In neutron stars in general, we don't have a good picture of what their magnetic field structure is. And those structures that we have built aren't stable, so they can't be the ones that are realized in nature. So that's a very interesting and peculiar thing. And it's, as I say, something that we really need to do better with in terms of our modeling. Again, I've spoken about sort of mainstream things that one can get bigger numbers if, again, one goes to other parts of the QCD phase diagram and allow for more exotic components inside your neutron star. So one of the phases that I talked about early on was the so-called color flavor lock phase. There's some other phase called 2SC. So I'm not an expert on these, but the point is you can then get a sort of a version of superconductivity that is bringing in not the electromagnetic, but the strong nuclear force. So again, you can get some really quite big mountains if these sorts of phases exist. And I did an estimate of this with my colleagues Kostas Glambadakis and Lars Samuelson back in. We found that you could be getting mountains, sort of magnetic CFL mountains, as big as 10 to the minus 7. Now, and this was for an internal magnetic field of 10 to the 12 Gauss, so that's not a crazy field. And that mu-q is something to do with the quarks, the quark chemical potential. So that is quite encouraging. As I say, we don't know how strong the internal field is. It's probably at least as strong as the external, could be significantly stronger. If you look at this plot on the next slide, what is it? So it's a graph of gravitational wave frequency versus gravitational wave amplitude. There are some noise curves on this. The advanced LIGO one is the red dotted curve. The third generation ET is the black curve. If you take the Vila and Crab pulsars and insert their parameters into the relevant formulae, you get numbers using this idea that are beginning to push into the ET detectability thing, at least for the Crab. So that's nice because just a plain old magnetic field in a normal star was just it was about 5 orders of magnitude below that, right? So you buy a lot if you allow for these rather exotic phases. So the Crab is interesting in this regard, the Vila, but probably not any of the other pulsars. These two are good because they're so young, they've got strong magnetic fields and they're not too far away. Okay. So that was all I was going to say about mountains, but there's more to CW source modeling than mountains. Let me just say a little bit about free precession. So what we've talked about so far is a neutron star, triaxial neutron star, spinning completely steadily about some fixed axis, and it gave off gravitational waves at precisely twice the spin frequency. So that's, really is the simplest sort of thing you can talk about. If you were then to take that star and kick it, perturb it in some way, you'd set it into free precession, sort of a wobbling motion. As well as being familiar from classical mechanics, this is seen on larger scales. So the Earth itself undergoes a free precessional motion. It's got a 14-month period. It's called the Chandler wobble after a person that discovered it. Free precession is actually a very interesting thing to model. My PhD many years ago now was about studying this. So if you've got a freely precessing star, it will emit gravitational waves. It has to, because of this wobbling motion. You're no longer spinning the mass around in an axisymmetric way. So you really do get gravitational waves out. It turns out that in that case, they come out at frequencies that are basically the spin frequency and twice the spin frequency. So they're coming at it two different frequencies now. The interesting and rather complicated thing about free precession is not just the gravitational wave emission, but the electromagnetic emission. So obviously this is a picture of the Earth here, and we're not interested in the Earth, right? We're interested in a neutron star. So a neutron star, if it's a radio pulsar, will have some axis fixed in it with a magnetic dipole sticking out. And as this star wobbles around, you can try and compute what the motion is of that dipole with respect to the inertial frame. And it turns out it's rather complicated because this wobbling motion itself is rather complicated. It consists, in fact, of two superimposed rotations. And it turns out that in all but special cases, if a radio pulsar was undergoing free precession, well, that would then show up as little modulations in both the time of arrival and the shape, and the polarization, all aspects of its radio pulsar emission. So radio astronomers have looked for this, and generally, well, there are some stars that are candidates for undergoing this, but there's no sort of commonly accepted candidate. So it looks at best that free precession is a relatively rare phenomenon. Let me go to the next slide. It looks like it's a relatively rare phenomenon. And this is why in lots of LIGO searches, or many LIGO searches, and particularly the earlier ones, they just, when they were, say, looking for gravitational waves from the Crab or some other known pulsar, those searches concentrated entirely at emission at twice the spin frequency. And it's because our radio pulsar colleagues are saying, look, we don't think that free precession is that common, so you probably won't get emission at 2 nu and nu, probably just at 2 nu. That's actually been relaxed a bit lately, and people are taking free precession more seriously. But as I say, it doesn't seem to be common. But if you do go searching for free precession, it's a bit complicated because it turns out that this gravitational wave emission is not at exactly the spin frequency and twice the spin frequency. There's some small offset. And so what you then have to do is perform one of these so-called narrow band searches. So a narrow band means that you're not assuming that you know exactly the frequency. So for the Crab, say, you're not assuming it's exactly 30 hertz and 60 hertz because you don't quite know what this offset is. You have to look over a little band of frequencies close to 30 hertz and close to 60 hertz. So these are narrowband searches. So they're not nearly as computationally as expensive as an all-sky search, but there is still some significant cost that goes with them. There's a caveat to this that's rather neat. Something that I pointed out back in 2010. We think that the neutron fluid inside all but the very youngest and hottest neutron stars is a superfluid. And there are reasons to think that in terms of the microphysics, how we think a neutron fluid should behave in terms of modeling it microphysically. But there's also evidence from things called pulsar glitches that neutron stars contain superfluids. And as I mentioned earlier, when a superfluid rotates, it does it in a rather funny quantum mechanical kind of way by forming a load of little vortices, that's little lines parallel to the rotation axis, about which there's some circulation of the superfluid. And that's how basically a quantum fluid like this mimics rotation. And it's believed, and this helps to explain glitches, that some rather unintuitive thing can happen, and these vortices can, in a sense, get attached or pinned to the solid bits of the star or to the magnetic field of the star. So people talk about there being pinned superfluids, and I won't go into it now because the details aren't sufficiently relevant to us, but this idea of having a pinned superfluid is crucial for explaining pulsar glitches. But anyway, the point of this is it's as if part of the neutron fluid, the part that's pinned, it's like a little spinning gyroscope inside your star. And if you move the crust around in some way, you have to move this spinning gyroscope around as well, because its vortices are pinned to the crust. So it's a rather unintuitive thing. But what I realized was, what it means is that if you have this additional degree of freedom in your star, if this little pinned superfluid gyroscope is misaligned with the rotation axis of the crust, the star can then spin completely steadily. So there's no sign of any modulation in the radio data, so it doesn't look like it's precessing, but it can nevertheless still emit gravitational waves, not just at 2 nu, like a triaxial star. It can also emit gravitational waves at the spin frequency nu. And so this has motivated LIGO and Virgo carrying out so-called dual harmonic searches, or even for completely steadily spinning stars like the Crab, you go searching at 2 frequencies. And if you look at the more recent targeted pulsars, the ones going after no neutron stars, you will see results presented for just this sort of search that allows for some emission at both nu and 2 nu, so both the spin frequency and twice that. This has now become a routine part of the LIGO Virgo analysis. So that's all I'm going to say about free precession and this closely related idea here with pinned superfluids. What I'm going to do now in the final part is talk about oscillation modes. So we've concentrated a lot on the magnetic field and the crust, but to a 0th order approximation, a neutron star is a ball of fluid, okay? And we know that self-gravitating balls of fluid, like the sun or other stars, have a whole complex zoo of oscillation modes. So oscillations with roughly constant frequency that just decay slowly. And when I say a complex zoo, what I mean is there are different types of oscillation modes. Some of them are mainly to do with pressure forces. Some are to do with magnetic forces. Some are to do with elastic forces. Some are to do with rotation. There's a whole zoo of these, as I say. And in principle, these, when excited, can emit gravitational waves. Now, some of these modes don't have anything to do with continuous wave emission. So, for instance, there's a famous mode called the F mode of a self-gravitating, of a neutron star. It's got a frequency of order of kilohertz, and it decays in about 0.1 seconds. And it's called F the fundamental because it's sort of the simplest mode, the one that's sort of easiest to calculate and we're most confident of. So that would be a burst-like thing, nothing to do with continuous waves. But there are other modes that could last a long time. And the mode that's attracted by far the most attention is the so-called R mode. And that's the thing that I'm talking about on this slide here. So what is it? So the R, well, some people say it stands for rotation, but most people say it stands for Rossby. So Rossby was a Swedish meteorologist that noticed these sorts of oscillation patterns in the Earth. I think it was the atmosphere, not the ocean, that he saw them in. They are modes where the the restoring force in the oscillation is the Coriolis force. So I hope you remember, right? The Coriolis force is a sort of a fictitious force that one invokes if you're doing Newtonian dynamics in a rotating frame. So if you were sitting on a rotating star, if you were to sort of kick it in some way, you would say that it's this Coriolis force that's causing your fluid elements to oscillate and providing the restoring force. So that's interesting enough in itself. It turns out that the frequencies of these R modes are to some approximation 4/3 of the rotation frequency of the star. And so for many pulsars, they're in a sensible range for LIGO and Virgo to look at. But the real reason why people got very interested in them was a discovery by my colleague Niels Andersen and Kostas Kokkidas that they can go unstable in a certain sense. And this is the so-called CFS instability. So that's Chandrasekhar, Friedman, and Schutz. They're the discoverers of the instability. And the story goes like this: so normally, if you've got a neutron star and you set up some mode in it, that mode, if you ignore things like viscosity, that mode will radiate gravitational waves and it will damp away. As I say, some of them damp away, on timescales of 0.1 seconds. Other modes might take longer, but they all emit energy as gravitational waves and they all damp away. So Chandrasekhar had done a calculation, and he went up to Kip Thorne and he said, Kip, does the gravitational waves always damp the modes in stars? And Kip says yes, and Chandrasekhar says, well, actually, no, they don't. Here's a counterexample. And he'd found a counterexample in a rotating star. And so the F and the S, the Friedman and Schutz, what they did was understand in a careful way what was going on. And it's a very nice little idea. And it's basically an example of a two-stream instability. So a two-stream instability, generically, it's a very general thing. If you've got two media, maybe two fluids, that can exchange energy between them. So an example, classic example here would be the ocean and the atmosphere. And they can, they've got a boundary and one can press on the other, so they can exchange energy. If you've got some sort of mode of oscillation like a wave that from, say, the point of view of the sea is moving from left to right, but from the point of view of the atmosphere is moving right to left, you can get what this so-called two-stream instability. It's sometimes called the Kelvin-Helmholtz instability in this sort of fluid context, where because of this mismatch, because where from the point of view of one fluid, the oscillation is propagating one way, but from the point of view of the other fluid, it's propagating in the opposite direction, the energy exchange between the two is unstable. It's called a two-stream instability. And what Friedman and Schutz realized was going on here was a sort of two-stream instability, where the energy exchange, in a sense, was between the fluid, the neutron star fluid, and the space-time. And so in this picture here, in fact, there are animations of this picture made by Chad Hanna and Ben Owen, but let's just look at this still picture here. This shows a neutron star. The idea is that if there wasn't an R mode on this star, all of these black curves would be circles. These little dots are just like little corks or little buoys floating, or little boats, say, floating on the surface. And because of the R mode, they get distorted. This is a rotating star. This pattern, if we were looking at an animation, we'd see it going round and round and round. So that would be us sitting in the inertial frame, and there'd be gravitational waves as a result. But if we were sitting in the frame of the star, we'd see that pattern going in the opposite direction. And it's this difference in the pattern speed between the inertial frame and the rotating frame that gives rise to the CFS instability. So that was a rather nice explanation for what was going on here. And the point is that for R modes, it's thought that this instability might actually occur in realistic neutron stars, and I'll say more about that in a moment. But it only makes sense in rotating stars, though, because these R modes only exist in rotating stars where you've got this Coriolis force as the restoring force. So in terms of why we think R modes are a good bet, what you can do is you can ask the following question. Okay, so there's a gravitational wave instability here. So if gravitational waves were the only thing extracting energy from the mode, then it would be unstable. But we know that in a realistic neutron star, you get dissipation from shear viscosity, from bulk viscosity, from something that you might not be familiar with called mutual friction, that's to do with energy dissipation in a superfluid. We don't need to go into details. The point is, there are all of these things tend to damp the mode. In other words, they act oppositely to the gravitational wave instability and tend to stabilize things. And it's still a matter of debate as to whether or not these damping mechanisms win out in neutron stars, or if the R mode wins out, and to what extent. And one of the ways of thinking about this is to look at this sort of curve here. On the horizontal axis, we've got the temperature of our neutron star. The vertical axis, we've got this spin frequency. And this is the so-called instability curve. And the idea is that at any given temperature, if your star lies above this curve, so F is greater than some critical value, then the destabilizing effect of gravitational wave emission wins out over the stabilizing effect of all these viscous mechanisms. And the reason why this is temperature dependent is that the shear viscosity is that these dissipation mechanisms themselves are temperature dependent. And it turns out at low temperatures, shear viscosity is strong. So this this low temperature portion of this instability curve is dominated by shear viscosity. Whereas it turns out that the bulk viscosity, so shear viscosity is the viscosity you get of having velocity gradients in a fluid. Bulk viscosity is the velocity you get by having volume changes. Bulk viscosity is stronger at these higher temperatures. So this right-hand part of the instability curve over here is dominated by bulk viscosity. And there are various microphysical reactions that could be important involving neutrons, protons, electrons, neutrinos, and possibly even strange things like the sigma minus hyperon there. So basically, there's a lot of interesting microphysics on the nuclear side that goes into computing these all of these dissipation mechanisms. And that's why I've not put numbers on this curve here. We're still not completely sure where to put the minimum in terms of temperature or spin frequency. And some people have, well, the experts still aren't completely agreed on this. This also is an active area of research, trying to figure out just where this instability curve really should lie. But you can make some fairly general statements just on the basis of this schematic thing here. So for instance, one of the pictures that people had early on is that a neutron star is born hot, so on the right, and fast, so top right. So it's born, I hope you can see my mouse, it's born somewhere top right. It then, in a matter of seconds to minutes, cools very rapidly through neutrino emission. So it moves to the left. It then enters the instability window. So what happens? Well, the R mode grows. And as the R mode grows, the R mode starts radiating energy away, and eventually it spins the star down. So as the star then cools further, its spin frequency decreases, and it follows some trajectory and exits this curve somewhere on the bottom left. And so the suggestion is that you could extract hundreds of hertz of rotational, well, you could extract a lot of rotational energy in the early life of a neutron star to entering this instability window and spinning down. It would then exit it somewhere over here. So maybe the young pulsars like the Crab and the Vela have been through this process, and that's why they've got relatively low spin frequencies. Another game that you can play is thinking not about young neutron stars, but about neutron stars in accreting systems. For those sorts of things, well, what did we say? Well, we said that stars get spun up in accreting systems. So maybe then your trajectory would be, well, at constant temperature, you start at small spin frequency and you get spun up, spun up, spun up. You're stable till you reach the curve. When you reach the curve, you then go unstable, and that heats the star up. So it moves to the right. The R mode grows, but then when the R mode gets big enough, it spins the star down again. So people have speculated you may get a sort of a cycle of stars in accreting systems. It takes hundreds of millions of years to do it, but they're moving around in some cycle there. So you wouldn't get steady emission, because once you enter the instability window, you then move in this cycle here. The situation would be different, though, if your accretion system is being spun up to the right of the minimum in this curve, because then you'd enter the instability window, heat up a bit, and you'd end up hovering somewhere around here. So that would be a way of really getting a long-lived continuous wave from an R mode in a low mass X-ray binary. So you can see there's a rather sort of rich phenomenology of what can happen here, depending on where you start off in this diagram and where exactly the minimum is in temperature and frequency. People think that neutron stars in accreting systems probably hit on the left, whereas if compact objects are in fact strange stars, so made out of strange matter, they're more likely to hit on the right. So there's a sort of a qualitative difference between those two scenarios. This in itself is a simplification, though, and people have gradually put in more and more physics into this and got more and more complicated curves, and they're not all simple monotonic U-shaped things. Well, this isn't monotonic, but they're not all simple U-shaped things like this. And they could have some complicated spikes in them to do with resonances. So the people in the St. Petersburg group have thought about that. So I think the bottom line here is we're still not completely sure how important, if at all, the R mode instability is, but it's still possible that it may be playing a role in setting the spin frequencies of stars, and it could be connected with long-lived gravitational wave emission. Okay, so I think those are all the important things I wanted to say. Let me just try and sum up then. So the first thing that we did was use some simple energy-based arguments to get upper limits on how strong gravitational waves might be. And the arguments ran differently depending on whether or not we're talking about targeted searches for things like the Crab, directed searches for things like, say, the Cassay supernova remnant, or all-sky searches. But one of the takeaways from that was that the LIGO-Virgo results are already interesting and have been interesting for some years now, in as much as it would have been energetically possible to have seen something. We haven't, but it would have been possible. But you need to look in more detail at neutron star physics and the microphysics and the nuclear physics to decide how big mountains could actually be in terms of neutron star structure. That's when we thought about elasticity and magnetic fields, but we've got a huge range of numbers depending on whether or not we allow for exotic phases and exotic cores in our stars. I talked a bit about precession and how maybe from the steadily spinning stars, maybe you get emission at more than just twice the spin frequency. If I had to sort of sum up, though, I would say that we're still pretty ignorant about what the actual realistic levels of mountains would be, or if the R mode's active. So it's still completely up for grabs, I would say, when the first continuous wave detection might occur. It could occur very soon. It could occur in 04, or it could be that it's many years away, and it could be that even ET, the third generation detector, won't be enough. I think we're that ignorant about the likely level of emission that we really can't be confident. But what I hope I have convinced you of from the second part of my lectures is that the interior physics of neutron stars is important in determining the level of emission. So if we do detect something, then as long as we can sort of say something like the inverse problem and infer what the emission mechanism was, we could stand to learn a fair bit about neutron stars. So that's it. I've got a couple of slides with exercises, but maybe at this point I should ask if there's anybody wants to ask any questions.
Gurudutt has a hand.
Okay, go ahead.
Yes, I have a question from the CFS instability. You showed us the curve. Yeah, this one. So there is a competition between instability and the stabilizing effects. So these three are the stabilizing effects: shear viscosity and bulk viscosity. So shear viscosity, we understand when the temperature rises, then this will go down. But what is not clear to me is the bulk viscosity, that why when the temperature rises, the bulk viscosity will be higher. I mean, that will be stabilizing the instability. And this mutual friction again, I mean, what is it? So if you could say a few words on mutual friction also.
Yeah, no, I'm happy
Yeah.
to do that. So with regard to the temperature dependence of the bulk viscosity, key point is this, that it's microphysical reactions that basically dissipate the energy, and this energy can get carried off by neutrinos, as you see in the first reaction. But the bulk viscosity is most efficient, it damps most rapidly if the time scale of the relevant microphysical reaction is close to the time scale of the oscillation. Because you get, I think resonance might be too strong a word, but the bulk, this is just a standard feature of bulk viscosity when you've got reactions going on, that the bulk viscosity is strongest when your reaction time scale is close to the fluid oscillation time scale. Now, the fluid oscillation time scale has got almost no dependence on temperature, but these microphysical reactions have got strong temperature dependencies. And so what's happening as you go to the right to higher temperatures here is you're getting closer and closer to a regime where the microphysical time scale is close to the mode time scale. And in fact, if you went to really, really high temperatures, probably too high to be relevant, there'd be another part of this curve that then comes down again, because you'd then be getting so hot that you're moving away from this sort of resonance-like feature. So let me ask, does that answer the first of your questions?
Yes, right.
Okay, good. And then the mutual friction, so what is that about? So mutual friction is a dissipation mechanism that is specific to superfluids. In fact, I think it's fair to say it's specific to superfluids. There's more than one version of it, but in the simplest one, if you've just got a rotating neutron fluid, then, as I said, it rotates by forming an array of vortices. These vortices themselves become slightly magnetized because of as the neutrons swirl around the vortex. So each vortex induces a 1/r velocity profile around it, whereas the cylindrical radius. So all the neutrons are swirling around the vortices. Because of an effect called entrainment, some of the protons are sort of pulled along as well, and some electrons, and so they become slightly charged. And then electrons can scatter off these slightly charged neutron vortices, and that's the effect that we normally think of as being mutual friction. So it's the scattering of charged particles off slightly magnetized vortices. And then there's a sort of a variant on it that people may or may not call mutual friction, which is that if, in addition to having neutron vortices, if you've also got superconducting protons, then the magnetic field of those protons forms magnetic vortices, and you can then get dissipative interactions between the flux tubes in the neutrons and the magnetic vortices in the protons. So that's sort of a variant on mutual friction. It's not terribly temperature dependent, though. Does that
Right. So so is it like that because we have multiple species, neutrons, electrons, and they are moving at different time scales? So this is a collision between the different kind of species, not with the same species. So can we consider this as a many multi-species fluid?
Yeah,
moving at different speeds.
I think all of the mutual friction stuff, and yes, and the bulk viscosity, because those reactions, they are sort of multi-fluid ideas. So yes, and in fact, modeling neutron stars as multi-fluids is something that we've realized it's a very important thing to do to capture these things.
Sure. So if these effects are there, so is it worth calling it a superfluid, because these effects are dominant, right? So then the notion of calling neutron star as a superfluid, I mean, does it still hold good?
Why would you not want to call it a superfluid?
Viscosity, right? One layer is not dragging the other layer.
I mean, it's a finite. Yeah. So I mean, it's true that when we I think I understand what you're asking. So when we normally think of a superfluid as completely dissipationless, right?
Right. Non-ideal effect are not there. Right?
Yeah, but the thing is, in any finite, even in the laboratory, in any finite temperature superfluid, you will get dissipative things going on. So some of the particles won't be in the condensate, and they can interact dissipatively. So I think it still makes sense to call it a superfluid because you've still got an array of neutron vortices, but it's not a perfect superfluid in that sense. So the vortices, because there's charged particles mixed in and they can scatter off it, and because it's at finite temperature, not all of the neutrons will be in the superfluid state anyway.
Right. Okay. Thank you.
Okay.
Because for superfluid, I think Reynolds number will be infinite, right?
Sorry, say that again.
For a superfluid, Reynolds number should be infinite, right?
Yeah, well, a zero temperature superfluid, everything would be in precisely the ground state.
Right. Thank you so much.
There's another hand up, but before that, I'd like to mention that please, participants, please feel free to attempt the questions which can be found in the folder, day one folder inside the Google Drive link. And in the meantime, I think, Supravo, you can ask your question.
Hi. So as you said that the R mode will be activated in this instability region. So this is mostly activated when young pulsars are cooling down. So I was asking if there are other physical scenarios where this instability region will be activated or the R modes can be activated, like during the inspiral or the post-merger.
Okay, so probably not the in-spiral, because so what you need, let me go back to the slide. You can still see my mouse. So in the in-spiral, the stars are probably, even if they're spinning fast, and they're probably quite cold. But in the post-merger remnant, you're probably kicked up to the top right again, right? Because if your post-merger remnant is a neutron star, it's probably spinning fast because it will have gained spin angular momentum from the orbital angular momentum, and because the two stars are smashed together, it will be hot. So it will be quite similar, probably, to having a newborn neutron star. So yes, in the aftermath of binary in-spiral, you could get the R modes being active, and that was one of the motivations for searching the LIGO data for such a signal, even though we know it probably wouldn't be detectable. But then the other scenario is precisely the one I spoke about with the accreting systems. So in an accreting system, you can start off at some reasonable temperature, like 10 to the 8 Kelvin, and spin up and hit the curve from below. And in that case, the R mode can also go active.
This is hand up by Arunava.
Hi, thanks, Sashri. Hi, Ian. Just a quick follow-up question regarding the crustal heating, probably deep crustal heating thing. What could be a possible mechanism that triggers this type of asymmetric heating, and what type of amplitude or say quadruple movement, asymmetric quadruple mass quadruple movement that we expect, roughly the ballpark range?
Yeah, so that's a good question. So in terms of why there would be an asymmetry, well, so that I think that the best thing I can say is the thing I mentioned on the slide, which is the magnetic field. So my student Emma Osborne ran with the following idea that if you have a magnetic field in a fluid, its thermal conductivity tends to be higher along the magnetic field lines than orthogonal to them. And that's just a consequence of the fact of how Lorentz forces work, that if you try and say push an electron along the magnetic field, it doesn't feel any force. Whereas if you try and move it sideways, it does feel a force. So the fact that there are magnetic fields in neutron stars mean that their temperatures can't be perfectly spherically symmetric because of this asymmetry that comes from the magnetic field. Now, the difficulty with this is that we actually think that the magnetic fields inside the relevant sorts of stars, the low mass X-ray binaries, are probably quite low. I mean, their external fields are no bigger than 10 to the 9 Gauss. So it may well be that their internal fields are at a similar level. And when you put the numbers in, then you get very small mountains, whereas the actual mountain size that you need, if gravitational waves were to play a significant role in these systems, it's more like 10 to the minus 7, 10 to the minus 8. So you probably need quite a strong internal magnetic field to produce that larger mountain. I've got another PhD student, Thomas Hutchins, who's looking at precisely this problem, but doing it with more realistic microphysics. And he's actually currently getting somewhat more encouraging results, but we're still working on that. But the bottom line is the magnetic field can induce some level of asymmetry in the conductivity and therefore in the temperature.
Thanks, Ian. We'll be looking forward to any new results. Yeah, thanks.
Okay, last question by Apratim. Then we shall move on to the tutorials.
Thanks. Thanks, Ian, again for the talk. I was just wondering if you can explain this phenomenon about the dual harmonic searches for glitchy pulsars. Like, I didn't understand why for when you have the spin superfluid, why searching at the spin frequency will be important. And also, I was wondering, like, is for this pulsars which show some glitches, is the recovery phase important in terms of gravitational waves?
Okay, yeah, I understand. I'm trying to find the slide.
37.
Okay, thank you.
Yeah.
All right. So the first part was, I think, what have superfluids got to do with getting a dual harmonic signal with both nu and 2nu coming out? It's somewhat unintuitive, but basically, if you've got a pin superfluid, it gives you a sort of an extra degree of freedom, and the total angular momentum of your star will then be the sum of two pieces. It will be whatever angular momentum is in this pin superfluid plus then the angular momentum of the rest of the star. And if you allow those two to be misaligned, then their sort of vector sum can still point exactly along the constant spin axis in space, but individually they're not. So it's as if you've got one vector like that and another vector like that, but they're adding to give something that points exactly along the z-axis. So you've got a fixed angular momentum, but this pin superfluid isn't pointing along that axis, and that in a sense breaks a symmetry. And so you're moving your mass distribution around in a way that would be different from a mountain, and it's that broken symmetry that gives you the emission at the two frequencies. That's not very intuitive. Another way of putting it is, if you take like a spherical shell, and it can be spherical for this to work, or some like oblate shell, but you just literally sew in a gyroscope that's then fixed to that shell, you would find solutions that spin completely steadily, but where that gyroscope isn't pointing along that steady spin axis. And that again is related to this dual harmonic thing. I'm not sure how clear that was. Did that help at all?
I didn't get an idea, but can you also like give me the reference to your paper, or is it explained there? Or
yeah, if you just look for Jones 2010, you'll DI Jones 2010, you'll find it.
Okay, sure. Okay, and also the recovery phase, does it play any important role?
Sorry.
The second part of the question, the recovery phase, does that play any important role? Like say in radio astronomy, you can model that, and that gives you some kind of a intuition about what leads to these glitches. Does that help in terms of gravitational wave, at least theoretically?
Yeah. So the possible connection between glitches and gravitational waves is an interesting one. There's been a bit of work on it, and I've got another PhD student, Garvin, who's just finishing his work that's looked in some things very relevant to what you just asked. So glitches themselves, probably to do with the unpinning of this pinned superfluid, and they may well cause the star to shake around and oscillate in some way. So you could immediately get like burst-like oscillations following a glitch. The numbers aren't very encouraging for how strong they might be, but that could happen. But then you do get quite long timescale recovery seen after many glitches, and that may be to do with superfluids or not. An alternative explanation for these recoveries is, in fact, it could be that you've got some sort of mountain that's created at the glitch that then decays away, the so-called transient mountain model. And my student Garvin Yim has got a paper out from last year, I think, that looks in that at detail. So there are potentially a few connections between glitches and gravitational waves. Generally, the numbers aren't very encouraging, and it's like a third generation thing, but it's certainly worth thinking about.